Hello everyone, I am Dr. Dhruvanjyoti Mondol and my channel name is Topics in Chemistry. Please subscribe my channel. I will discuss different topics of chemistry in this channel, so please subscribe my channel to get latest notification. Today I am going to discuss part 9 lecture of phase equilibrium, and the topic name is binary eutectic phase diagram. So the last lecture I told you that there are mainly three types of two component systems phase diagram: type 1, type 2 and type 3. In type 1 I've told you that here two components, say A and B, they simply mix with each other and there is no reaction between these two components. But if you consider type 2, here the two components, say A and B, they react and they form a new component, and this component will have a stable melting point. This melting point is called congruent melting point. Okay, for type 2 it will have a congruent melting point. That means the new component, new compound, stable up to its melting point. Now if you consider type 3, here also like type 2, A and B react with each other and they will form a new compound, and this compound will have a melting point which is called incongruent melting point. Remember, here the new component is not still up to its melting point. So this is the three types of two component system phase diagram: type 1, type 2, type 3. Today I'll discuss type 1 phase diagram. So this is the heading: characteristics of type 1 simple eutectic phase diagram, binary eutectic phase diagram. So what are the characteristics of type 1 simple eutectic phase diagram? Number one point, that's the most important point: two components do not react with each other. Number 2 point, two components simply mix with each other in the solution or in the molten state. Number 3, this is the most important point. Here the two components will form a mixture, and in that mixture they will mix with a particular proportion. So this is called a proportional mixture. So the proportional mixture of two or more components that melts or solidifies at a single temperature. Remember, here at a single temperature, here the two components actually melts or solidifies at a particular temperature, remember, which is lower than the melting point of any components. Okay, so this mixture is called eutectic mixture. Okay, one example is given. Suppose lead silver system is one example. There are many examples. One example is lead silver system. So now we have to know what is the type 1 simple eutectic phase diagram, and you have to draw the simple eutectic phase diagram. So before that, you have to know what is the cooling curve of a pure compound. So now consider this is a pure compound. Okay, so in that compound, suppose here is a pure compound, it is in the molten state of, suppose the compound name is A. Now, if cooling is done on this compound, gradually you can see crystals of A will come out. Okay, so here is the crystals of solid A. So here liquid is converted to solid A. Okay, so A is the name of the compound. Now you have to show, you have to know actually what is the temperature versus time curve for such type of cooling. So here you can see this is the first state, A is the first state, and here you can see you have to, with increase of time, if you decrease the temperature, so here cooling is done, so with increase of time, if you decrease the temperature, first the temperature of the liquid A decreases. So here you can see with increase of time, the temperature gradually decreases. At B, here the first solid of A comes out from the liquid solution, liquid molten state of A. So here the first crystals comes out, and you can see the temperature is almost constant. Temperature is constant here. So through a BC, gradually you can see the solidification of A continues, and at C the solidification ends, and after C you can see again the with increase of time the temperature decreases. That means the cooling of solid A occurs. So in brief, first you can see this is the A point. Here the cooling of liquid A starts. So if you see the AB curve through the AB curve, the cooling of POA occurs. If you see B point, the B point stands for solidification of A. So here the solidification of A starts, at through BC you can see solidification of A continues, and you can see here the solid A. Remember here solid A is in equilibrium with liquid. At C point solidification of A ends, and through CD cooling of solid A occurs. Okay, so now you have to know what is the degree of freedom. The last lecture I told you here you have to use a reduced formula of degree of freedom. Why it is reduced formula? Here actually the pressure is constant. Here you can see liquid is converted to solid, so pressure change is very negligible. Okay, that's why here you have to consider this formula F is equal to C minus P plus 1. It is not plus 2 because here pressure is constant, so you have to subtract 1 from the actual formula of degree of freedom, C minus P plus 2. Okay, so that's why the formula is C minus P plus 1. Now if you see through this line, what is the degree of freedom? F is equal to 1. Why is F is equal to 1? Here you can see it is only one component system. So it is one component system. Here all are liquid state or molten state. So phase is equal to 1. So 1 minus 1 plus 1. So F is equal to 1. So here is the degree of freedom. F is equal to 1. That's why you can see with increase of time, gradually the temperature decreases. Okay, the temperature changes occur. So only 1 degree of freedom, only one variable is present here. So now if you see the BC line, the BC line actually the degree of freedom F is equal to 0. Why is F is equal to 0? Already I told you that here the solid A is in equilibrium with liquid. Solid A that means solid is one phase, liquid is another phase. So here the phase number is 2, component is 1. So 1 minus 2 plus 1. So it stands for F is equal to 0. F is equal to 0 means there is no variable. Okay, there is no variable means here you can see the temperature is also constant. That's why F is equal to 0. F is equal to 0 means pressure constant, temperature, there is no variable. That's why it occurs, the solidification of A occurs at a particular, a fixed temperature. After C point, you can see the F is equal to 1. Why F is equal to 1? Here you can see the all are solid phase. Okay, so P is equal to here only 1, P is equal to 1, C is equal to 1 plus 1, so F is equal to 1. So again you can see there is only one variable. So this cooling, the cooling of solid A depends on only one variable. So with increase of time, you can see the temperature gradually decreases. So it depends on temperature variable. Okay, so this is the cooling curve of pure compound. Now you have to know what is the cooling curve of a mixture. So first consider, suppose this is a mixture. Here it consists of two components, one is A and another is B, and they are in the molten state. And remember here the amount of A is greater than amount of B. Now cooling is done on that solution. So first, as you see here, the amount of A greater than amount of B. So first, the solid of A appears, solid of A crystals out from the liquid mixture, and again the cooling is done. After some time, you can get the mixture of solid A and solid B. Now you have to know what is the cooling curve of such type of mixture. So it is given here. So suppose the A is the starting point, and you can see through AB actually the cooling of mixture is done here. Okay, so you can see through AB cooling of mixture is done here, And at B, you can see the crystals of A comes out from the mixture. So here you can see at B, solidification of A starts. And now through BC, you can see solidification of A continues. So here the solidification of A continues. And remember here, through BC, solid A is in equilibrium with the liquid. And here you can see the liquid is converted to solid. So this is actually a exothermic process. So here heat is released. So this heat is called heat of solidification. And for that heat, the process is very slow. It is not a very fast process. The process is very slow. Okay. So actually for heat of solidification, the process is slow. At C point, you can see the solidification of B starts. So here through CD actually, both the solid A and solid B, both are in equilibrium with the liquid through CD. Okay, remember that. At D point, solidification of A and B ends. After D point through DE, cooling of solid AB mixture is done. Okay, so here the cooling of solid, here the the D line stands for cooling of solid AB mixture. Okay, so this is the cooling curve of a mixture. Now you have to know what is the degree of freedom for such type of process. So again you have to use this formula, F is equal to C minus P plus 1 reduced phase rule formula. So through AB line you can see the only one phase is present. So one phase is present means P is equal to 1 or the liquid phase, and here component number is 2, so 2 minus 1 plus 1, so that gives you 2. So here degree of freedom F is equal to 2. Next, if you consider BC line, here you can see solidification of A starts. That means here through BC actually you can say that the mixture contains solid A. So this is one phase, liquid, this is another phase, and so number of phase is equal to 2. Component is 2. So 2 minus 2 plus 1, that gives you 1. So F is equal to 1. That is for BC line. Now consider CD line. Okay, so in this CD line, as I told you that here that point, the C point, solidification of B starts, and as I told you that here A and B both this solid is in equilibrium with liquid. Okay, here both this solid A and B are in equilibrium with the liquid. So number of phase is equal to solid A, solid B, and liquid. So total phase 3. So phase is equal to 3, component 2 plus 1, that gives you is equal to F is equal to 0. Now you can see here D line here solid, number of phase, there is no liquid phase, all are solid. So phase, that means solid A and solid B, two phases. So number of phases is equal to 2, component 2, and so 2 minus 2 plus 1, that gives you 1. So this is F is equal to 1. Now you can see through CD line F is equal to 0. So there is a non-variant system. So non-variant system means there is no the cooling of AB, that means the crystals when the both are equilibrium, solid A and B both are equilibrium in liquid, that means they're not dependent on any variables. Okay, so that's why here the crystallization occurs at a particular, at a fixed point, at a fixed temperature, crystallization occurs. But here you can see BC line, it here EF is equal to 1. So it depends on temperature variable. So with increase of time, temperature gradually decreases. Okay, so it is not a fixed temperature. Now here it is ought to mention that here B is the starting of solidification of A. So now if you see my last slide, here I have here you can see the cooling curve. So in the cooling curve here, first B point stands for the solidification of A. So this is the freezing point of liquid A. Okay. So now if you consider the next slide, here also B stands for the freezing point of liquid A. Okay. But remember here the temperature, it is lower than the previous slide. Okay, so here the temperature actually decreases. So you know the colligative property, depression of freezing point. In the first case, the mixture, that is the cooling curve, a pure component, pure solution, pure compound. But here it is a mixture, and you can see the amount of A greater than B. So it is not a pure compound; it is impure compound. So depression of freezing point occurs. Okay, so that's why the depression of freezing point occurs. So here the temperature is lower than the pure compound, pure compound A. Now you have to know what is the simple eutectic phase diagram. So before that, here I have told you the last two slide what is the temperature versus time plot. Now you have to convert it into a temperature versus composition diagram. Okay, temperature versus composition diagram. Now suppose this diagram is for a pure compound. Already I have told you this is for a pure compound. First temperature decreases. Here the first compound A, pure A comes out, and temperature is fixed. Then this is the cooling of pure A. So this is for a pure compound, pure component. Okay, and this is the freezing point. This point is for a freezing point of that pure compound. So here you can see it is given here in the temperature versus composition diagram. This point stands for the freezing point of pure A. Okay, now suppose the name is given, suppose the name is given is A. Okay, the name is given is A. Okay, name is A. Next, here now we have to consider it is a mixture. So it is a mixture means here it is a mixture. So it is a mixture, so this is the freezing point now. So here the freezing point decreases. First initially this is the freezing point, but now this is the freezing point. So freezing point depression of freezing point occurs. So this is the freezing point of pure A, and gradually the temperature decreases, and at that point A and B solid, these two solids are equilibrium with the liquid. So here this is a mixture. This is for a pure compound, pure component, and this is for a mixture. A, B is in A. So the amount of A is greater than amount of B here. So now you can get this is the freezing point, and here the composition of A decreases. So first case this is a 100% composition. Here is all are pure A, but now this is not a pure A. Here pure A, here A it is a mixture. So you can see this is the point. This point. So here it is the amount of A. Okay. So this is not 100% pure A. Okay. So now this is the freezing point of A. So this is the freezing point of A. Here this is the temperature. So this is the next point. So this point is given. Suppose the name is given is here. The name is A prime. Suppose the value name is A prime. Next you can see again amount of B here increases. Okay, amount of B increases. So this is the again the freezing point depression occurs. Freezing point again decreases. So this is the next freezing point. So again the here again the A compound freezes out. Okay, so A compound freezes out from the mixture. So now here you can see at that point both A and B are in equilibrium with the mixture, with the liquid. So here is the composition given here. So this is suppose the name is given here. It is suppose A prime, A double prime. Okay, so here you can see gradually the temperature of A, freezing point temperature gradually of A decreases, and you can see also the composition of A, composition of B actually, composition of B increases. Okay, so this is 100% pure A, and you have mixed some amount of B in A, so the freezing point depression occurs. Freezing point of depression of freezing point of A occurs, and this is the new composition of pure A. This is the new composition of pure A, at that composition. So this is the freezing point. Now consider pure B. Okay, so this side the pure B is given. So this is the pure B, and this is the melting point of pure B. So this is the melting point is given here. This is the melting point of pure B. Suppose this point name is capital. So this is the capital B. Okay, so now what I have to do? You have to now this is the for pure B. Now you have to mix A in B, and when you mix A in B, freezing point depression of B occurs. So here this point stands for the freezing point of B, and here it is not pure 100% pure B. So you will get the point here. Suppose the point you will get the point here. Now suppose the name is given. Name is B prime. So then this is the value. So it is B prime. Next you'll get this is the next point. This next freezing point. Here the amount of A now increases in B. So again the freezing point depression occurs, and the composition, suppose this is the composition here, this is the composition of B. So you'll get the point, the next point, the next, suppose the point is B double prime. So B double prime, you'll get the B double prime here. Okay, so this is the 3 point. First depression of freezing point of A occurs, and as gradually the composition of A decreases, and here this is the pure B. When you mix A with B, gradually the freezing point decreases of B, and also the composition of pure B also decreases, and A amount increases. Now if you join these two lines, if you join this A prime, A double prime, and if you join this B prime, B double prime, then you can get this two line. Okay, you can get this two line. Okay, now these two line meets at that point. This point is named as O, which is called eutectic point. Okay, so at that point the freezing point of A is equal to freezing point of B. Okay, so at that point freezing point of A is equal to freezing point of B, and if you see it will form a new mixture. Here both component freeze out at a fixed temperature. So here you can see the diagram of eutectic point is given here. Both the component freeze out at a particular at a fixed temperature. Okay, so this is the curve. This is the temperature versus time curve at the eutectic mixture, at the eutectic point. Therefore, you'll get the line, you'll get the eutectic phase diagram like this. And now suppose we erase this point, A double prime, A prime, erase it. Okay, so this is the point now. So A, this is the first point, first freezing point of pure A. This is for 100% pure A, and this is the first temperature is T1, and T1 temperature gradually decreases, and composition of B gradually increases, or you can say the pure A amount gradually decreases and B increases, and this side gradually A increases, and you can see the pure B amount decreases. So first this is the freezing point of pure B. When you add A and B, freezing point decreases, and this is the new composition. Again you add A and B, again the freezing point depression occurs, and this is the next composition. So now you have to join this line. You can, these two line meets here. This point is called O, called the eutectic point. Now this is in short the phase diagram of binary eutectic mixture, phase diagram of two component system, type 1 two component system. So in brief, this side is the temperature and this side is the composition, and that is for pure 100% A, and that is pure 100% B. Now if you see here, this is 100% A, this is 75% A, 50% A, 25% A, and this is 0% A. Now if you consider pure B, this is 100% B, 75% B, 50% B, 25% B, and this is 0% B. So if you go from this side to this side, gradually the amount of B increases, but if you go from this side to this side, amount of A increases. Okay, so amount of A this side increases and amount of B if you go this side to this side increases. Now, you know that the phase diagram consists of some point, line, areas. Okay, so you have to know what are those points, what are those lines, and what are those areas, and you have to also know what are the degree of freedom of this point, line, and areas. So first consider the points. What are those points? So first, if you consider the point, the first point is given is here A. So this is the A point. So A point is the freezing point of A. And you know that the freezing point of A, that means this is a fixed temperature. This is a fixed temperature and here A is equal to 0. Okay, so already I have told you why it is F is equal to 0. And you can see the temperature versus time diagram of the cooling of a pure compound, and there I have told you that why it is F is equal to 0 using the rule C minus P plus 1. Now if you consider this here, this point, this is another important point, this is the B point, here also this is a fixed point, so this is the freezing point of B and it is also fixed temperature, so this is F is equal to 0 also. Now consider this point O point. So O point means this is called eutectic point. Here remember this is fixed temperature and it is also fixed composition. And here also F is equal to 0. Okay, so these are the three important points A, B and O, and in each case you can see all cases F is equal to 0. Okay, now you have to know what are the lines. So you can see here, first you can see this is one line AO or OA line. So through AO line you can see gradually the composition of A decreases. So here actually the temperature of freezing point temperature of A decreases. So this is called, that's why it is called freezing point curve of A. This is actually the liquidus curve. Here the in each point one liquid molecule converts to solid molecule. Okay, of A. And here also you can see degree of freedom F is equal to A. So if why is F is equal to A? Again I have told you that in the previous slide that the previous slide, this is the temperature versus time plot of the mixture. There I have told that why it is F is equal to 1 using the rule C minus P plus 1. Now, if you consider this BO line, so already I have told you that B is the freezing point of B, and through this line, gradually the freezing point of B decreases, and so this is called the freezing point curve of B. It is not A, it is B. Okay, so freezing point curve of B. And this is called liquidus curve. Liquid is also a liquidus line. So here the each point the B freezes out, B solidifies from the liquid mixture. So here also F is equal to 1. Now if you consider this CD line, this is the CD line. Okay, so here A and B, both A and B crystallize out from the liquid. So here A and B crystallize together from liquid. So now it is not liquidus curve. Here all are solid. So this is called the solidus curve. Okay. So here also each point the degree of freedom F is equal to 0. Okay. Now you have to know what is the areas. What are the areas present here? This is one area above AOB line. So above AOB line, you can see all are liquid, and here also here remember the F degree of freedom F is equal to 2. Now if you consider this AOC area, if you consider this AOC area, here you can see solid A is in equilibrium with liquid, solid A is in equilibrium with liquid, so here F is equal to 1, degree of freedom F is equal to 1. BOD area, here in this area here you can see solid B is in equilibrium with liquid, solid B is in equilibrium with liquid, so here also F is equal to 1. And if you consider here this area C, D, E, F, here solid A and solid B are present, and here this is the eutectic mixture. Okay, here the degree of freedom F is equal to 1. So these are the points, lines, and area of binary eutectic phase diagram. Now, suppose if you consider a line here at 75% of A and 25% of B. Okay, so you have considered here a line. So here A amount is greater, and this line. So suppose you start your journey from that point, from P point. If you go gradually, if gradually decrease the temperature, then the line will cut this liquidus curve at Q point, and this line will cut the solidus curve at R point. So when you can consider this Q point, at that point actually the solid A converts to liquid. Okay, and you can see through this line the composition of A gradually decreases. Okay, now if you see this line cut here at R point. So at R point you can see both solid A and solid B that are in equilibrium with liquid. Okay, so here as first A crystals out from the as A solidifies from the liquid mixture, that's why the amount of A is greater than the eutectic mixture. Okay, the amount of A is greater than eutectic mixture. Now consider another line here, another line. So here you can see it is 25% of A and 75% of B, or B of 75% of B. So here you can see amount of B greater than amount of A. So now if you consider, if you start a journey from X point, if you gradually decrease the temperature, this line will cut this liquidus curve, BO curve at Y point. Okay, at Y point. And again, if you decrease the temperature, this line will cut at Z point. So up to Y point, this is the change. Gradually, that the amount of B decreases. Okay, so now if you see that this Y point, at that Y point, you can see the one on B solidifies from the liquid mixture, and at that Z point, A and B, both the solid, are in equilibrium with liquid mixture. So this is a eutectic mixture. So here again you can see as first solid B crystals out from the liquid mixture, so the amount of solid B is greater than amount of eutectic mixture. Okay, so these are the defined points, line, area, and degree of freedom of binary eutectic phase diagram. In the next topic, I will discuss what is the phase diagram of type 2 two component system and type 3 two component system. Thank you. Finally, my request to my students, please subscribe my channel. Thank you.